All goes on one big ball.
All right. All right, people, are we good? Are we good? We've got ourselves now in the zone. We're gonna try and learn something that's not related to ball jokes, right? Good. Okay, who enjoyed the lab? All right, good.
We like playing with the balls.
I knew that. Somehow I thought you might. So anyway, it's a good lab. It's fun. It's weird. It's very messy, but it's a lot of fun. All right. So thank you for keeping it relatively clean. No thank you to whoever smeared stuff all over my dining room table, but I'll get that. All right. So today we're going to start touching on organic chemistry. So this is the chemistry that kills a lot of people. I'll be honest with you. This is the chemistry that a lot of the times you get to college and you do organic chemistry and you're rethinking your life decisions. It can be very difficult. We are just brushing the surface. I told the juniors this morning that when I did organic chemistry, I think back on it as a class that I made it through by the skin of my teeth. Like, oh my gosh, I barely passed that class. It was so hard. But when I look back at my transcript, I got like a B, which it doesn't feel like it should have been a B. Because I left that class like, bleh. The thing with organic chemistry is it's less conceptual and more memorizing and mounds and mounds and mounds of information that is strangely similar, which makes it hard to differentiate what you're memorizing, right? So we're going to touch on it today, but first thing, when you're talking about organic, if you see the word organic in a grocery store, like these are organic apples, what does it mean? Like, what are they getting at? Caitlin. It's alive. Okay. What else?
It's either living or it was living.
Living or was living. Now, I'm asking if you see it in the grocery store. Liam.
It costs 3 times more.
It costs 3 times more is true. That is true. Why? Colin.
They haven't, no pesticides have been used on it, and they're not genetically modified in any way.
There you go. That's what we're getting at. Okay. So the idea is if you see something in a grocery store like a tomato or an apple and it's listed as organic, they're trying to tell you that they've used naturally occurring pesticides or no pesticides and naturally occurring fertilizers like manure versus a chemically synthesized fertilizer. It may or may not be genetically modified. If you are being a stickler for the term genetically modified, pretty much everything you eat has been genetically modified. Has anybody ever seen what wild corn looks like?
Yeah.
What's it look like?
Grass.
Grass. Yeah. Looks like grass with a couple of little nubbies on it that might potentially be something you could eat if you bred it. So most of what we eat has been genetically modified because of selective breeding, which is a type of genetic modification. Now it's different than doing gene insertion and that sort of thing, but it's still pretty much everything is GMO. So that's one of those terms that you got to kind of watch when you see it. Like, what is it really telling you?
Did you know they bought a...
I was about to ask. Yeah, who knows about the wolf, the dire wolf? Did everybody see this week? Yes?
Got it.
So they took a...
Jurassic Park.
Yeah, exactly what it is. So they took a wolf that's been extinct for 13,000 years called the dire wolf. And apparently they talk about him in Game of Thrones. I don't know. I don't watch the show. But they took this wolf and they wanted to bring it back. So this company took a gray wolf and edited its genome and put in the genes that make the gray wolf different from the dire wolf. They put the dire wolf genes in, which in turn created essentially a dire wolf. So now there are dire wolves that have not been around for 13,000 years, and we have them. And did anybody read what they want to do next?
Woolly mammoth.
Woolly mammoths!
Yeah.
I'm not so sure any of this is a good idea.
This is...
That's my question. What were you going to say, Colin?
That's the thing. If they did make Jurassic Park, I'd still totally go. I would go.
I would go too.
The thing is, Jurassic Park isn't very realistic because we went to the aquarium and they said that like predators will not hunt if they have food available. Like hunting is what they do. So Jurassic Park, like the dinosaurs wouldn't have done that if they were already being fed.
That's a good point.
I
I don't know why they chose the dire wolf. One of the concerns is that, you know, habitats, there's a pecking order, there's a food web, and that if you insert something new into it, you're gonna have a problem. And this occurs every time we get an invasive species, right? The Joro spiders. Joro spiders everywhere now, just like 2-3 years ago they arrived, right? So we have these Joro spiders and our birds don't eat them. They don't eat them at all because they're like, what is this? And then the Joro spiders, fortunately, will eat the brown marmorated stink bugs that also came from Asia. They were also invasive, but not much else. Kaden, what were you gonna add?
Do you think they can bring back the fairness?
I don't even know what that is. Do you think they would? I don't know. There's so many things they could bring back or not bring back, Caitlin. Oh, the wolf puppy. Okay, Caitlin is right here. The wolf puppy is adorable, but still. Okay, Lucas.
Are they released? Wow.
That's a good question. So Lucas asked the question I had. Are they gonna release these wolves into the wild? I kind of hope not, because we have a system that's balanced.
They need to go to the zoo.
Well, and then the problem is, why create them to keep them in captivity? What are we doing? So ethics are a thing, Colin.
Also, a quick point, Real Jurassic Park, actually, we can't bring back dinosaurs because all the DNA has degraded, almost 65 million years.
Yeah, there definitely is some degraded DNA. The problem is, we can do gene editing where we can go, I think I know what that was, and pop that in. Yep.
How do they know they created a dire wolf? Like, is there any like?
They have some DNA. They have, obviously, they must have had one that was preserved enough to get DNA from it. So, yeah. Can you have a pet dodo? Yeah. We'd like to bring back the dodo. Okay, so back on our topic. So when you see the word organic in a grocery store, it usually refers to how something was grown and produced, right? It's done more quote unquote naturally. I always have problems with those words because they say it doesn't have any chemicals. Never mind, it's composed of chemicals, but you know what I mean, right? Right. So colloquially, that's organic. Now, organic, when we're dealing with chemistry, is living things, carbon-based compounds, right? So these words are different. When you see organic in the store, it's completely different than organic in the sense of chemistry. So organic chemistry can be very challenging. Today, we're going to see why. It has mostly to do with the fact that there are a million names for things. And if you do organic chemistry, you pretty much are expected to memorize them all. And it's a lot. That's the challenge for most people. All right, so compounds of carbon, anything with carbon in it, we're going to call these organic compounds. So we have allotropes. Does anybody know what an allotrope is? We're going to start with allotropes. Do you know, Colin?
Different arrangements that an atom,
Liam?
a certain atom can arrange itself.
Yes. So it's each of two or more different physical forms in which an element can resist. So an example would be graphite, charcoal, and diamond. These are all allotropes of carbon. The carbon atoms in these compounds, they all contain only carbon, but the atoms in the compounds are arranged in such a way that the structures are different. So graphite is what's in your pencil lead. It's not lead, it's graphite, right? And then a diamond is what I got on my left hand. These are the exact same chemical, but they look completely, I could not write with this diamond. In fact, I could cut things with the diamond, you know, because diamonds are very sharp. They're very hard. They're like one of the hardest substances we have. We test things against diamonds all the time. But when it comes, and you have to cut diamonds with other diamonds.
Yeah.
Like when you shape them, that's what you do. You cut diamonds with other diamonds. So diamonds are very, 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 very hard. You can also put them under UV light and they will fluoresce. Carbon doesn't, graphite doesn't do that, right? Well, in a minute, I'm going to show you what the structure, the actual model, guys, no, actual model of these different structures, and you'll see why you can write with one and not the other. So the properties of carbon allotropes, for example, depend on the arrangement of the atoms and how they're bonded. So allotropy is the property of some chemical elements to exist in two or more different forms or allotropes when found in nature. Okay, so not lab, but nature. Now, yes, you can create them in a lab, but typically we're talking about these are natural forms. And there are several allotropes of carbon. Now, we just discussed a couple. We said graphite. What else did we say? Diamond.
Coal.
And coal. Okay, so, but if you look, these are what we're dealing with. So diamond is A. Everybody see A?
Yeah.
See how that looks almost like a Lego arrangement or something that would be very sturdy and very strong. B is your graphite. Now, do you see why you can write with that? Look at it. It's like little planes, right? Little flat chunks. And if you drag it along a piece of paper, they're going to fall off and leave a nice little trail, basically, which is what they're doing. So you can see why you can write with graphite and not a diamond, right? And then next to it, you've got Lonsdaleite, you've got C60, which is Buckminster fullerene or buckyball. Look at that, D. They call that a buckyball. It sounds like something you get at a really cool gas station, but it is not. If you look at H, it's a single-walled carbon nanotube, which they call a bucky tube. So you have buckyballs and bucky tubes. These are all carbon atoms. Different ways they arrange. You've got C540 for E or carbon 540. F, you got C70. G, you have amorphous carbon. This is more like what you're dealing with coal. So it's kind of like diamond, graphite, coal. And you can see there are other arrangements that you can get to. All right, so this is a quick video, but it's going to, if it will play, I'm going to have to turn the volume up since I turned down AC/DC because they were blaring at us. But
You have options within options. That's Lauren Decor.
yeah, Lauren Decor.
Your life is your choice. Choose your next move at WGU.
All right.
You have a choice to make.
In today's video, we're going to learn about the structure and properties of two allotropes of carbon, diamond and graphite. And we'll consider the other allotropes, graphene and fullerenes, in the next video. First though, you might be wondering what an allotrope is. Basically, allotropes are different structural forms of the same element in the same physical state. So if we consider carbon in the solid state, it can take lots of different forms, like diamond, graphite, or fullerenes. So these are all different allotropes of carbon. Both diamond and graphite are giant covalent structures, which means that they're made of a regular lattice of covalently bonded atoms, which makes them both very strong. In diamond, each of the carbon atoms is covalently bonded to 4 other carbon atoms, which is the maximum number of bonds that carbon can make. This forms a regular 3D pattern, which you're fortunately not going to have to draw, but you do need to be able to recognize this sort of structure. As each of these covalent bonds is really strong, it will take loads of energy to break them. And so diamond itself is very strong and has a really high melting point. However, it doesn't conduct electricity because it has no free electrons or ions that can move around. Now, let's compare these features of diamond to those of graphite. First, each carbon in graphite is bonded to only 3 other carbon atoms, rather than 4 in the case of diamond. Second, the atoms are arranged into hexagons that together form large flat sheets, which are then arranged on top of one another to form lots of layers. However, these individual layers are only held together weakly, as there are no covalent bonds between them. This means that they're free to slide over one another, which makes graphite relatively soft when compared to diamond. That said, graphite still has a very high melting point, because the individual layers are strongly held together with covalent bonds. Now, do you remember how earlier we said that carbon atoms can make 4 covalent bonds each? But in graphite, they only make 3. Well, that means that each carbon atom in graphite has 1 spare electron that it's not using in bonding. Instead, this electron becomes delocalized, which basically means that it's free to move around. And all of these free electrons allow the graphite to conduct electricity and heat. Before we finish, it's worth mentioning that a single layer of graphite is known as graphene, and scientists can actually isolate these individual layers and use them to make other structures, such as spheres and tubes. We call these structures fullerenes, and we explore how they work in the next video.
Which we aren't going to watch the next video. All right, so let's talk about hydrocarbons. So these are the simplest organic compounds, and they're composed of only 2 elements, which are what and what? BJ.
Water and carbon.
Not water and carbon. You got one of them. You got one. Hydrogen and carbon, hydrocarbons. So if you look, we have examples of different hydrocarbons here. Now you've got one carbon with 4 hydrogens, 2 carbons with 6 hydrogen, 2 carbons with 4 hydrogen. And what you get here, if you notice the names, methane, ethane, ethene. This is your first taste of, oh, the fun naming in organic chemistry. Do you notice the similarities in the names? Okay. It's because there are big trends for how to name. Guys, if I have to, one more and somebody's moving. Don't distract me or anybody else, okay? So they're similar, but they're different. It's like the same but different. So when you see it, it's almost like a dichotomous tool where it's like, if it's not this, it's that. If it's not that, it's this, that kind of a thing. And we'll get there in a minute. But this shows you some examples of some of these hydrocarbons. Now, it's the same 2 elements, right? But they're structured differently each time. So you're going to get, oh, by the way, these are all gases. Flammable too, fun. Yeah. So this is where we start our categorizing. All right. So, and this is just the surface of organic chemistry, but you've got hydrocarbons into 2 groups. Your first group are called aliphatic. Within the aliphatic, there are saturated and unsaturated, and they get grouped into one of these. The 3 types of aliphatic hydrocarbons get grouped into saturated or unsaturated, and I'll show you a flow chart in a minute. But they are hydrocarbons based on a chain of carbon atoms, so a chain. And we have our 3 main types. So you have alkenes, alkenes, and alkynes. Okay, we see the similarity in the naming, but the difference, here's where it starts to get fun. So your alkanes are aliphatic. Okay, Liam, can you come up here? Because you're right in the middle, and it just takes one person out of the equation there. Not that it's you in particular, you're just the one in the center. All right, so your hydrocarbons are based on chains of carbon atoms, like we said. These are aliphatic. Your alkanes have only one single covalent bond. Your alkenes have at least one carbon-carbon double bond. And your alkynes contain a carbon-carbon triple bond. So canes have a single, kenes have a double, kynes have a triple. So alkenes, alkynes, single, double, triple. Occasionally you find an aliphatic hydrocarbon with a ring, and those are called cycloalkanes. Cyclo, because it cycles in a ring, right? Thank you. And alkenes or alkynes, it kind of depends on what type you're dealing with in the first place, what your bonds are. So that's group 1, aliphatic. Your group 2 are aromatic. That's a fun word. Aromatic hydrocarbons. Great example is benzene, or a flat ring system that contain continuously overlapping p orbitals. Remember our orbitals, S is 1 is P, right? And the electrons in the benzene ring have a special energetic property that give benzene physical and chemical properties that are markedly different from alkanes. So your aromatics are in a ring as opposed to your aliphatics, which are in a chain. Now, even aromatic and aliphatic sound similar. They rhyme. They both start with A. That's helpful. And then you get alkenes, alkanes, alkynes, which all start with A and have very similar endings. So this is where the challenge is for most people with organic chemistry. It's all of the memorization that's necessary to be good at it and quick and not have to like look something up with a flow chart every time. So originally the term aromatic was used to describe a class of compounds that were particularly fragrant. But now, and they are very fragrant. And now in modern chemistry, though, the term aromatic denotes the presence of a very stable ring that imparts different unique properties to a molecule. So again, it's one of those words that, you know, doesn't necessarily mean what it used to mean, but we still use aromatic. And in chemistry, organic chemistry lab, when you get to work with aromatics, you know you're working with aromatics. They really do have a very strong smell. So here's how the little flow chart would work. So we have our hydrocarbons, right? Remember, we have aliphatic, aromatic. This side says acyclic. What would acyclic mean? No ring, right? Not in a ring, in a chain, acyclic. Acyclic or aliphatic, which is typically what we call them, aliphatic. Now, if you have two groups that are saturated and unsaturated, well, sorry, saturated and what do you suppose one would be then?
Saturated.
Saturated, right? Yeah, saturated, unsaturated. Your alkanes are saturated. Your alkenes and what? Alkynes are going to be unsaturated. Okay, that makes sense. Now, if we come over here to this side, cyclic or closed chain. So cyclic. What do you think 3 would be? What do you think?
Aromatic.
There you go. Okay, so we have our aromatic. They also have these alicyclic ones. We're not even touching on those in this class, but you have your aromatics, and they're going to be non-benzenoid. And what do you suppose? Benzenoid. Okay, and remember benzenoid, we talked about it being a ring. All right, and these it's like a ring of carbons kind of all together. And you'll see in a minute, there are going to be some prefixes that deal with numbers, like penta is how many?
5.
And what is 6? Hex. Okay, so you start seeing it. Now, when you've probably even seen, like if you read the back of your shampoo bottle, you'll see things that say like hexa, whatever. You ever seen that? And you're like, what is that? That's where those are coming from. Those names are coming from these types of structures. And they tend to be the ones that are like this long on the back of your bottles of cosmetics and hair stuff and whatever. And you look at it and you're like, oh my gosh, what is that? And that's why it's so long, because you have to take all the different characteristics of the molecule and you put them in a specific order to get the name. So this, like I said, this is where the challenge is for most people. So this is where it gets to be a lot of information, more than that first bit. So we have what are called functional groups. So organic compounds are going to be classified by their functional groups. Okay, and these are functional groups. Oh boy. So think of it like this. Think of it like this. You have a series of hats, okay? And if you put on one hat, it's a chef's hat, you're a chef. If you put on a nurse's cap, you're a nurse. If you put on a firefighter's hat, you're a firefighter, right? So basically, if I took my firefighter hat and put it on Yusuf, now he's the firefighter, right? Because it's the hat that makes you the firefighter in this analogy, all right? That's kind of how these work. It's like a tool or a hat or whatever that sticks on that molecule that then gives that molecule its characteristics. So you can take these base molecules and add the functional groups, and because of the functional groups, they're going to function similarly. So think about how this could be useful in something like pharmaceuticals. You know the end result you want. You want to affect this system or this process within the body. Okay, well, I know what functional groups to use. Now, what bases do I pop them on to create what I'm looking for? And beyond just the functional groups, there are, it's almost like patterns or layouts. So I'm going to give you an example. Let's say that this is molecule A, okay? And the shape of it is what's going to let it function this way. Okay, this is not molecule B. This is an isomer of molecule A. You've taken molecule A and you've basically mirror imaged it or flipped it in such a way, it's going to function similarly. Best example of an isomer in your modern day situation that you probably have come across and didn't even realize you came across it. You guys were old enough when COVID hit, most of you, that you probably remember the argument over ivermectin. Anybody remember that? Anybody hear the argument over ivermectin, or was nobody paying the slightest bit of attention? Okay, most of y'all were like middle school, so all right, so ivermectin, during the COVID pandemic, when the world was shut down and we were all kind of losing our minds and getting a little ridiculous about some things and not so ridiculous, what I decided I was about to give up the day I read an article that talked about virus particles and masks. And I'm like, what is a virus particle in the first? Oh, no, I'm sorry, virus molecule. That's how it was stated. The virus molecules, I'm like, viruses are made of many molecules. You can't call it a virus molecule. I'm not even going to read the rest of this article because you've lost me already. Like, I've lost all respect for you. You have no idea what you're talking about. I'm not going to go any further with this. But he was talking about whether or not virus molecules could fit through what type of mask material. And I'm like, already already we are scientifically illiterate and I'm not going to go any further. Okay, so ivermectin is a veterinary medication. It's used on large livestock, horses, cows, things like that. And there was a subset of people, a population of people who were claiming that ivermectin could be used to treat COVID. I think it actually works with parasites in those animals, but I could be wrong. Anyway, yeah, James is nodding, sound right? Yeah. So anyway, it's a veterinary medicine. And ethically, you shouldn't go giving veterinary medicines to people because you're supposed to test things before you just go willy-nilly give them to people. But there were people that were getting and taking ivermectin and swearing up and down that it was going to fix the problem. And then there were other people who were panicking over that, going, are you out of your mind? You can't take cow drugs, like in the pandemic. What are you doing? Well, anybody remember the name of the pill that came out that like everybody was getting handed? Paxlovid? Anybody take Paxlovid? I took it once. So Paxlovid was the very quickly, probably not anywhere near typically tested like we usually do, medication that we rolled out and started giving to people when they got COVID because it did make it go way faster. It made the long COVID less of a thing for people. Okay, essentially, this is ivermectin. This is Paxlovid. There is very little difference between the two. But now we've got an isomer, which is pretty much the same function. It's just shaped a little differently, oriented a little differently. They actually call them left-handed, right-handed, that sort of thing. And now we've rolled it out for people because we've remarketed it. But essentially, the ivermectin people weren't really wrong. So they weren't really ethical in like drugging people. Yeah.
So people weren't exactly wrong in saying some of the COVID medicine just wasn't tested.
No, it definitely was not tested the way things are typically tested. No.
They just kind of.
If you've ever tried to get a drug tested in the market, it's typically years and years of testing that's required. And that was absolutely not done with the vaccines or the medications because it was like, we are under a state of emergency, let's roll it out. And it's interesting because it makes you wonder, it's one of two situations. Either the testing that we do is probably in some ways, maybe too much, at least when it comes to trying to get a med to the market so people can use it, or we took stuff that wasn't tested enough. It can't be both. You know what I mean? They rolled it out fast. So, and I know plenty of people who have tried, been in drug trials for medications, and then those drug trials, in the end, they don't get enough good results to support what they're trying to support, and you can try and stay on it with compassionate care, like you can get an exemption and take this untested drug, but that's hard to do. A vast amount of the medications that pharmaceutical companies produce do not get through the testing process and don't get to us. And the ones that do, if you've ever watched a TV commercial, how many side effects do they tell you it's going to cause? Everything causes diarrhea, first of all. Everything causes diarrhea. You know, memory loss, blah, 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 blah. There's 9 million, and those went through years of testing. So when you think about it, no, that stuff that we got definitely did not go. But here's the thing, though. Even though you can say maybe Paxlovid wasn't tested as much as it should have been before humans got it, ivermectin was tested for years and has been used successfully on animals. Whoop, whoop. Not that different, right?
Literally every medicine commercial is like, here's one way this thing can help you.
Yep.
Here's 50 ways it can kill you.
Oh, yeah, absolutely. Absolutely. And you may have also heard another good example of isomers is you may have also heard and this is because this is the high school group, I can say this, but cannabis products, right? Okay, so cannabis products, now there are products that are accessible under federal law that are Delta 8, Delta 9, all these different deltas. They are all isomers of THC, essentially. They're slightly flipped, slightly structured different than the THC, which is the psychoactive part of the cannabis product. But they exist in different types of cannabis. That's not just marijuana cannabis. They exist in hemp cannabis, and they can be derived from hemp cannabis, which is not federally illegal, but marijuana cannabis is, but science is faster than the government. So now you can buy these other versions. Yep. So, I mean, it's just one way that it's like science is speedier than legislation. And there we go. She says. All right. So organic compounds are classified by their functional groups. In organic chemistry, a functional group is a specific group of atoms or bonds within a compound that is responsible for the characteristic chemical reactions of that compound. The same functional group will behave in a similar fashion, undergoing similar reactions, regardless of the compound to which it is attached, basically. So functional groups also play an important part in organic compound nomenclature. Nomenclature is a naming process. Combining the names of functional groups with the names of the parent alkanes provides a way to distinguish the compounds. So functional groups are often used to functionalize a compound, affording it different, what do you suppose? What kinds of properties is it going to give it if you add a different functional group to a compound? Chemical and physical, right? And that it would have in its original form. So you take your alkane by itself, it does certain things, it reacts in certain ways, you pop a functional group on it, now it's going to act like that functional group. You take a different compound, you pop it on, it's still going to act like that functional group because the functional group is what's doing the work. So functional groups will undergo the same type of reactions regardless of the compound of which they are a part. However, the presence of certain functional groups within close proximity can limit its reactivity. So functional groups can be used to distinguish similar compounds from each other. So if you look, these are just some examples of functional groups that are used in organic chemistry. Ketones, aldehydes, amines, thiols, arenes, and these all get attached to your alkane, for example, and you just kind of, they can pop it on, like I said, like a hat. Ooh, these are slow to load today. Here we go. A little bit on functional groups. Woo! She got into med school. Good for her. Here comes your organic chemistry classes.
Obviously, affordable tools. You want hard-afforded tools. As we've already discussed, hydrocarbons are molecules
Why are we in the
containing
middle?
only carbon and hydrogen. You will learn the definition of a hydrocarbon and how functional groups give molecules similar
Mockingbird.
properties. Organic chemistry is the study of carbon compounds. There are many millions of organic compounds that you can make using hydrogen and carbon and arranging them in different ways. Hydrocarbons are defined as compounds made of hydrogen and carbon only. The simplest hydrocarbon is methane. It consists of one carbon with 4 covalent bonds to hydrogen atoms. The next in the series has 2 carbon atoms, and this is called ethane, and is followed by propane and then butane, these being the names of the first 4 in the series of molecules called the alkanes. Pause this video now and try to draw the structure of hexane.
I'm not going to
Hexane
attempt to draw it,
has
just
6
watch.
carbon atoms.
Think about what could happen
Use
with
the
those
structure of
6.
hexane. Compare it to the structure you drew. Did you get it right? The
Hex
next
6,
series
there you
is
go.
called the alkenes. These are hydrocarbons that contain a double covalent bond between 2 carbon atoms in the molecule. Just like the alkenes, each carbon atom still needs 4 bonds, but has 2 bonds already due to the double covalent bond with the other carbon atoms. The ethene molecule is completed by 2 more bonds with 2 hydrogen atoms for each of the carbon atoms. These also follow a pattern, and the next molecule in the series is propene and then butene. Pause this video now and try to draw the structure of hexene. As before, hexene has 6 carbon atoms.
So how are they going to be bonded? If it's an ene, not an
Here
ane.
is the structure of hexene. This
Double
time
bond.
there is a double bond because
One.
it's an alkene. The video tutorial on the alkanes and alkenes will give you more in-depth knowledge on the bonding and structure of these series of molecules. As we have already discussed, hydrocarbons are molecules containing only carbon and hydrogen atoms. However, the study of organic chemistry includes any molecule with a carbon backbone. Functional groups are groups of atoms which give molecules similar properties. There are many different functional groups. You may have heard of the alcohol group. This is a hydroxyl group and is a hydrogen bonded to an oxygen, which is then covalently bonded to the rest of the molecule. This group can be attached to any of the alkane to form alcohols, their name all ending in -ol. For example, methanol, ethanol, and propanol. Pause this video now and try to work out the name of this molecule.
Okay, this one I will pause. What do we think it is? We know it's gonna end in -ol, right? Quadol? What do you think? Caitlin, do you have a guess? That one's methanol. Okay. All right, let's see.
There are 4 carbon atoms in this molecule with an alcohol group, and so its name is butanol.
Oh, that one's not so
Alcohol
easy.
functional group
Butte.
means that all these compounds will react in a similar way and will have similar properties. Carboxylic acids are another example of a functional group. This is the functional group for a carboxylic acid and gives an organic molecule the name oic acid, methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. There are lots more functional groups. Esters, which give molecules a sweet smell and
They
make them
really
useful
smell.
for perfumes and
Smell
flavourings.
like bananas sometimes.
Ketones, which make molecules useful as solvents. Amines, which can be used as dyes and useful in making medicines. Some molecules have more than one functional group and give molecules different properties still. Now, by the end of this video, you should know that organic chemistry is the study of carbon-based molecules, and that hydrocarbons are molecules containing hydrogen and carbon only. You should also know that functional groups are groups of atoms which give molecules similar properties.
So they showed you ethanol, methanol. So you used ethanol today in lab, right? 50% ethanol. So like if you're distilling, say you decide you're gonna be one of those hillbilly guys that, you know, do the the moonshiners, right? All right. So when they're out and they're distilling, they're producing different alcohols, not just one. They produce a methanol and an ethanol. And they have to know in the process how to keep the methanol out, because you can drink the ethanol, you cannot drink the methanol. The methanol is poisonous. The ethanol, you have to drink a lot of it. It will eventually be poisonous. Anybody who's ever seen or heard of alcohol poisoning understands that, right? But methanol and ethanol don't act the same way in your body.
These guys are just unemployed chemists trying to
Yes,
earn.
they kind of are. They kind of are.
They're smart.
They are smart. Yeah, there's a lot of chemistry involved. A lot of chemistry involved.
Good trying to make their own beer.
And that's distillation, which is different from what you're talking about is fermentation. And there is fermentation with distillation. Distillation is a second process after fermentation that gives you spirits like vodka, rum, moonshine. But beer and wine are not distilled, they're just fermented. And there's chemistry in that too. Actually, I saw there's a lady on Instagram, she's called the Appalachian Forager. And I saw her a video, I guess she reshared it from like last year, but she's taken that invasive Chinese wisteria and making it into fizzy soda pop. And like the first thing she mentions is, you know, you pull the flower, she calls them flowers, she's real Southern, but you pull the flowers off the bloom, but you don't rinse them because they have naturally occurring yeast, and that's what you need to get the bubbles to make your drink fizzy. Shit, the whole thing, I'm gonna try it.
So Andrew and I took this nature class.
Uh-huh.
Where the guy basically like told us about like surviving in the wilderness, and he actually like showed us how to do that. Like we actually, I don't know what, even though we actually kind of did that.
To distill water or to distill?
We made like a soda.
Okay, yeah, you can make like a soda. Yeah, you can do it with all kinds of stuff. This lady, if you look her up on Instagram, Appalachian Forager, she has one for pine soda and one for wisteria soda. And she's drinking like pine soda with like lemons and lime slices in it. It looked very refreshing. I'm not sure how much I'd like pine soda though. Like I don't know. I don't like gin that tastes like a pine tree that's distilled from like juniper berries. So
I've seen a guy make ice cream out of several different kinds of wood.
oh, that's fun. Okay, yeah. I don't know.
Yeah.
That's all right. This morning I saw a thing about a restaurant in Copenhagen, y'all, that gives you like a 12-course meal and it includes live bugs a couple different times. But it was like, and this represents the plastics in the ocean. And it was like, I don't know, some kind of gelatin jellyfish wrapped in edible plastic wrap looking like stuff. It was very creative. I don't want any of it. All right, names of structures. Here's where it gets real fun. All right, so naming, how do we do it? Oh, organic chemistry. The names of what are the basis for the names of most hydrocarbons? Do we know? You know? She's gonna guess. Adam, okay, which structures do you know? Anybody? Good. Functional groups, he says. All right, so yeah, we're doing with alkanes is how we start with most of them. And then yes, you add in your functional groups. So look at this one real close. All right. Identify the root. Identify the longest continuous chain. And then find the root name for the number of carbons in the chain. And then you identify the suffix. This is the stuff that makes organic hard for people. So your longest chain has 6 carbons. So your root name is going to be hex. And it's an alkane. So your suffix is going to be ane. So it's hexane. And then you're to look at like whatever functional groups are stuck on it. And then that's how you go about putting the name the name together. And here are just some examples. Oh, here we go. For example, right there. Meth is 1, F is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, dec is 10. That's how we go about putting in our prefixes. Oh, it disappeared. Oh no, it does that. Yeah, the TV was like, I can't take it anymore. This is too much.
It's even too much for the.
I'm not going to expect you to. What are we doing? There you go. To memorize this stuff. If you take organic chemistry in college, and any of you that are doing anything STEM related that has to deal with biology or chem, will take it. Good luck. Good luck. Yes. This is coming your way. You're completely capable. Like I told you, I feel to this day like it was the hardest class I ever took, and I feel like I failed miserably, and I didn't. I got a B. I just felt like I was failing every day because it's challenging. But some people walk right in and they do it. I will say this, the labs in organic chemistry are some of the most fun labs. They are really fun labs. They're very involved, but they're very cool. It's a lot. It's a lot of information.
More fun than making balls.
I remember specifically. So here's the thing. Collins is very small. And once you're in a major and you're out of your freshman year and you're probably like by second semester of sophomore year, you're with your group. Like this is the group you're going to do all your classes with. This is the group you're going to graduate. They were like, I want to say there were about 25, maybe 30 of us in my class that were bio majors. And we were in every class together. Oh, his ball came apart. Oh, James. Oh, James broke his ball. Anyway, so you get to know your professors really well because it's the same professor that's teaching you 3 or 4 different classes. Because it's not the kind of school that's so big that's like this person teaches neurobiology and that's all this person teaches. No, they teach several things. You get to know them very well. So the chemistry professors we had were Bansi Kalra, who I absolutely forget. His first name was much longer than Bansi. It was like this long, but he shortened it to Bansi. Bansi Kalra, Dan Derringer, and Sandy Boatman. And Bansi Kalra taught intro chem. So a lot of non-chem majors that needed their science credit would take his class. And he's the guy who would turn on the burners and throw chemicals at them and carry on about how they were his favorite. And he had like a really thick accent, so it was like entertaining as heck because he was like, "I'll throw this on here." And then, "Oh, I love strontium." Throw on the strontium. And one time I lit my shoe on fire, and you're like, "What is this man? He's crazy," but he's so fun. Dan Derringer, much chill. Dan Derringer had a daughter named Danny, so she would hang out, and she was like 9. She thought it was cool that there was another Danny. That was fun. Sandy Boatman was the only professor I had in 4 years that I didn't love. There are some professors when you get to college, even if it's a nice small little school, there are some professors you're going to get who are not the best teachers, but they're real good at research and they get grant money, so they have a job. even your smallest schools, and you're gonna run into these people, and she was one of these. I don't think she liked teaching at all. I think she wanted her grant money, she wanted to do her research, and she loved it. She confused me and my classmate Amy Paris all the time. We don't look that much alike. She told me once what she said, oh, your retake on your test, because Amy had been sick or something, like in the hospital. And she's like, that test you got or whatever, and told me the score. And I'm like, I didn't take a test, Dr. Boatman. She's like, oh yeah, the other one, and walked off. So that made the class even harder. So if you get a challenging class and you get a professor that's like not a lot of fun, it makes it even harder.
What accent did he have?
He was Indian, but he had like, it's like a South Indian accent or whatever. And he was just so fun. I love Bonsi. He was the best. And everybody called him Bonsi. Nobody called him Dr. Cholera. He'd look at you and go, don't call me that. So he was just Bonsi to everybody. Yeah. Dr. Derringer, Dr. Boatman, Bonsi. Wait a minute. Shh, I can't hear Caden. What? Yeah, she did. She called me the other one. She was not super. Not mean, just not warm. But she gave me one compliment, and I remember it to this day because it was the only like nice thing she ever said that was, I mean, she wasn't mean, but it was like out of her way to be nice. A lot of organic chemistry is reactions that involve color changes, like we've done this year. And we had to describe the color, and people would write pink, and I would write watermelon because that's a specific shade of pink.
Yeah, put it back in.
Y'all good? And so she once told me that my colors were the most descriptive she'd seen in years. And I thought, okay, maybe she'll remember who I am now, but she didn't. So anyway, all this is all memorize. You don't really want to go through these flow charts, these dichotomous tools. You want to know it. You want to be able to understand it when you see it. And as you can tell, it's a lot. It's a lot. So that's where the challenge is. But if you get a good professor, a good study guide, good study partners, you should be able to do it. Nope, if I can do it, you can do it, right? That kind of thing. So it's just challenging, but you can do it. So how do we model these compounds? We have different options. So most of what you've seen so far are the structural formula models, right? That's what I've been showing you all morning. These little guys. Look at that. Methane. Remember I said meth is 1, eth is 2, right? So methane, ethane, ethene. Why is it ethene, not ethane? It still has 2 carbons, but it has what?
Double bond.
It's got your double bond. Exactly. Right. So now, you know, by looking at it, all right, that's not ethane, that's ethene because it has the double bond. And you can use your ball and stick model if you want. That's a little more complicated. It's certainly more complicated than it is for, like, if you're going to sketch it out, you're going to use that. And then there's also these space-filled models. These are more like your computer generated kind of dealios, but these are what you would do the most. You'd be sketching them in your notebooks, and you've probably seen, like, they make like artistic chalkboard versions of all that now, where you see all the molecules drawn out. Like I even have a dress that has it on it, that kind of thing. It's fun. They're easier to sketch and see. So what kind of reactions do organic compounds have? So we have, oh, and let me tell you one more thing. Some of these molecules are so long, especially these chain molecules can get so long that they have to be folded to function. So proteins are the best example of that. Proteins are very, 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 very long molecules, and they literally fold up like origami, and they make a specific shape when they fold, and that shape impacts how they interact with other things. And you can denature a protein, which means you're basically unfolding it, and that then you can do different things with them, like in a lab if you denature. And when you cook, that's what happens too. Like you denature proteins with heat or certain chemicals. But yeah, they're big, long, and they fold up. So these are not little molecules. This is not like H2O, little things that we've been dealing with, NaCl. These are big, long molecules. So you can have a substitution. And this is an atom or a group of atoms is going to be replaced in a substitution. So there's an example. You can have an addition, which is where an atom or a group of atoms is added to replace a double or triple bond. And there's just another example. See the little ring? That's what we're talking about, benzenes. If you've ever seen diagrams of molecules with that little hexagon, that's where you start talking about aromatics, benzene rings, and things of that sort. There are a gazillion of these, and they all have different little groups on them, and you have to be able to name them all. Yeah, it's tons of fun. And then you have elimination. And this is a pair of atoms or group of atoms are removed from a molecule, usually through the action of acids, bases, or metals, and in some cases by heating to a high temperature. So it might look like that in the end. These are all just different examples. I'm not going to make you like draw them for me or anything. Now, condensation. When we talk about condensation up to this point in your scientific career, you've talked about a phase change from, or stage change from what to what? Gas to liquid, right? Condensation is gas to liquid. Condensation in organic chemistry is completely different, but you can kind of think of it like when you have a nice cold glass on the table and water gets added to the outside of the glass. That's condensation. In chemistry, it's a molecule, usually water, is formed by combining atoms from adjacent carbon atoms. You've added a water, it's called condensation. Nothing like the condensation you've been familiar with forever. It's kind of one of those terms, like oxidation, you know, like am I adding an oxygen? Am I taking out an oxygen? We did a redox, right? So condensation is adding water. So it's definitely a different situation. All right, now, polymers. So let's have a look at the word polymer. Do you see a root or a suffix or a prefix you know? Caitlin? Poly means what? Not more, but how many? Yeah, kind of, yep. Multiple, yeah, it means many, right? A polymer is many, all right? So a polymer is what? It's a large what? A very large what, James? Yeah, it's a very large molecule. And it's made up of chains or rings of linked repeating subunits, which we call monomers. Mono means one. Poly means many. So you make a chain of many by single units of one, right? A link's in a chain. There's one link, two links, three links. Together they make a chain. All right. Polymers usually have high what? Anybody want to guess? Melting and boiling points. Because molecules consist of many monomers, polymers tend to have high molecular masses. These are very heavy, large molecules. So today in class, you created polymers, right? These molecules are big, long. You can see, look at this one at the bottom. That is a big, long molecule. Look at the one at the top. Big, long molecules. It's not like a little H2O, little NaCO, any of the stuff we've done so far. Big, long molecules. And they're all little subunits that come together. So we said poly means what? Many. Did you have questions separate, or you were just answering that? Okay. All right. So poly means many. What do you think mer means? Do you know? Substances. Good guess. Parts. How'd you know that? Many parts. Okay, good. That was a good guess. Yeah. So parts. All right. Polymer, many parts. Monomer, one part. Put one part, one part, one part. Now you have polyparts, right? Many parts. So that word is a perfect example of if you know your roots and your suffixes and your prefixes, you can decode the word. So mer means parts. The word was coined by a Swedish chemist, and this is a fun one. He's Swedish, so how do you suppose his name is said? Jan Jakob. Yes. This is actually Berzelius is a pretty well-known chemist. He's sort of a fixture, Berzelius. So Jan Jakob Berzelius, 1779 to 1849. So in 1834, he came up with our word polymer, right? And although with a slightly different meaning from its modern definition, most things change over time when we get a better understanding of what we're dealing with. And the modern understanding of polymers as macromolecules was proposed by German organic chemist Hermann Staudinger in 1920. So what's a macromolecule? Yeah.
A big one.
A big molecule. What if it was a small molecule? We would call it a micromolecule, right? There's again, macromolecule, micromolecule. Anybody ever use like the macro lens on the camera, like the, you know, on your iPhone camera or whatever, you can like zoom in stuff. Actually, the Bird Buddy people that make my cool camera bird feeder have one now that's they have a Kickstarter or something like that for it, and it's called Blossom. And it's a small little camera that has one of those. Yeah, have you seen it? Yeah, and it'll show you like bees or hummingbirds that come to your flowers. Like you can put it in your flower garden and watch videos of the bees and stuff. That's gonna have to be my next thing because I love the birds, but bugs are cool.
It's the macronutrient tracker app.
Okay, there you go. Macronutrients. So large amounts, large things, macro large, micro small. So these are macromolecules. They're huge, huge big molecules. And like I said, the proteins, for example, are so large they have to be folded up. They're giant. All right, now this is actually I'm going to give you like a little heads up on both your homework, and I'm going to show you kind of what the juniors are learning for their homework because it's a little different from yours. But you're going to look at this alternative assessment, and I'm going to actually give you some of the answers now, so you're going to kind of want to pay attention. But it's about dimethylmercury. So it's an organic compound that poses a serious environmental threat to all living things. What kind of a threat? We're going to talk about that in a minute. But research how this compound affects living things. We're going to talk about that a little bit in a minute. You're going to have to do some additional, right? And include information on whether dimethylmercury poses a threat to your local environment. And if so, determine what's being done to eliminate the problem. All right, mercury at room temperature is what? It's a liquid, right? But do you want to play with it in your hand? You want to run? Why not? It's toxic, right? It's toxic to you. Now, my mom still talks about how when she was a kid, if a thermometer broke, they would play with the mercury like until they just lost it all over again. Because yeah, they did. I mean, it was totally a thing. There used to be mercury thermometers everywhere. Now most of our thermometers are digital or they're alcohol. Like we use alcohol thermometers in lab. We don't use mercury thermometers. But mercury can be made more harmless. Like you get mercury glass, like this stuff right here. You've ever seen this before? You know, it's where they've taken it and they've made it, used a process where they can coat the inside of the glass. You get that cool kind of mirrored effect. You've probably seen mercury glass around. But in the past, mercury was used in a lot of medications, which obviously caused people problems. And we're going to talk about one particular population of people and the problems they had due to exposure to dimethylmercury. And you might know where it came from. You may have heard this before.
Oh yeah, the hat was from that because of me over using a hat.
Why is that Mad Hatter? Why is Mad Hatter a phrase? Okay. Because where's the mercury coming from?
The hats.
Well, yeah, but where's it? Where's it coming from? Do you know? Do you know?
The fabric on their hats themselves or something, right?
Yeah, but where are they getting the mercury? Not cold mines. Do you know?
Johnny Depp.
Johnny, it's going to be grosser than that. Well, we'll watch. You'll see.
Pigs.
Close.
Okay.
I'm here to sing it.
Heard. Whatever.
Carol Fay and Clark children's books, Alice's Adventures in Wonderland. A quirky character is featured who is known as the Hatter. He's described in the tale as mad, and his eccentric behaviour came to earn him the popular title of the Mad Hatter. However, the term mad as a hatter, sometimes used to denote a person with bizarre or erratic behaviour, was not invented by Carroll. Instead, the descriptor is associated with an occupational hazard of the then hat-making industry. The mad and strange behaviours were caused by mercury poisoning. During the 18th and 19th centuries, hatters, also called milliners, used a noxious chemical called mercury nitrate for processing the pelts of small animals like rabbits in creating felts for hats. In those days, there was...
So just real quick, couple things. Milliner came from, that word comes from people who imported fashion items, often from Milan, milliner, and they're using mercury nitrate. You're going to look up dimethylmercury. Similar effects, however. Think about where you might find nitrate.
Little protection of workers' health and safety, and it was well known that long-term exposure to the toxic mercury fumes caused damage to the nervous system. The result was that many of these skilled craftspeople suffered from particular physical and mental illnesses. Their symptoms included speech disorders, erratic mood swings, hallucinations, psychosis, and tremors, which were known as Hatter's shakes. The mercury-induced twitching, also called the Danbury shakes, was in the city of Danbury, Connecticut. Danbury was the foremost bastion of the millinery industry during the 19th century and was dubbed the hat capital of the world well into the 1920s. It was then that the demand for headwear declined with the rise of covered vehicles such as trains and cars. Workers' rights also became important, and in the US, the use of mercury in felt production was finally banned in 1941. Historians have theorized that Boston Corbett, a hat maker who dispatched President Abraham Lincoln's assassin, may have sustained mental health impairment caused by his mercury exposure. Corbett was a professional milliner from a young age. Following the tragic loss of his wife and child in childbirth, he converted to Christianity and became a religious fanatic. However, his faith was characterized by erratic behavior, which researchers attribute to a background of probable mercury poisoning. Corbett's religious zeal caused him to proselytize amongst his fellow workers, grow his hair long like Jesus, and take up strict preaching. His eccentric behavior became dangerous when in 1858 he performed self-castration with a pair of scissors as a means of suppressing his libido. In
That's fun.
1861, he enlisted in the Union Army to serve in the American Civil War. Again, his behavior caused him problems as he persisted in sermonizing amongst his troops, even reprimanding superiors for bad language. He landed in the lockup for insubordination and was even court-martialed.
So real quick, this mercury made him crazy enough to not only be a religious zealot, but to castrate himself with a pair of scissors. Everybody know what that means?
Cut off his balls.
Cut off his external genitalia.
Just balls. It's different for the babies.
Likely. We've had a lot. Yeah, that's a eunuch. We've had a lot of balls today. Yes. Removed his external reproductive genitalia because he thought it would suppress his libido, aka his sex drive. So mercury can make you crazy is the point, right? Because that's pretty crazy. All right.
Destined for execution until the sentence was reduced and he was discharged from the army. However, Corbett immediately re-enlisted and in 1865 found himself in the 16th New York Cavalry, which had been sent to track down President Lincoln's assassin. After slaying Lincoln on April 14, 1865 at Ford's Theatre in Washington, D.C., Confederate sympathizer John Wilkes Booth had gone on the run. By April 26th, Corbett and his regiment had Booth surrounded in a Virginia tobacco barn. The Secretary of War, Edwin Stanton, had given strict orders that the fugitive was to be captured alive. However, Corbett later admitted to disobeying orders and claimed responsibility for the downing of Booth. Again, he was arrested and court-martialed, but on giving his questionable account of events, was pardoned by Stanton and called a patriot. Other witnesses contradicted his story, and the farmer and his son even swore that Corbett did not even reach for his gun. However, he was generally acclaimed as a hero by the public and press for his part in avenging the president's untimely demise, and rewarded him with a princely financial sum.
It can't buy back what he cut off.
To employment as a hatter, Corbett was regularly fired for stopping work to pray for sacrilegious colleagues. He still operated as a Roman preacher and even gave public lectures about the Booth incident, complete with lantern slides. However, he was increasingly discredited and ostracized due to his incoherent ramblings, paranoia, and erratic behavior. He got into several fights, and in 1887 was committed to an insane asylum after turning on officers at the Kansas State House where he was working. 15 months later, Corbett was able to escape the asylum on horseback and apparently lived out the rest of his days as a solitary homesteader in
Probably for
Pine
the best.
County in eastern Minnesota.
Now it said, and that's fun, creepy. So it said mercury nitrate was what the milliners were using to help.
Stiffen the hat.
Yeah, it's for use. It's how they process the felt. Okay. Mercury nitrate. As things got better economically, there were probably some more acceptable sources of mercury nitrate. But if we back it up to the Industrial Revolution area, what was the economic situation for a lot of people? Yeah, it was pretty poor. So you'd be willing to sell anything you could sell to make money. What might you sell that has nitrate in it?
Wait now.
Not poop, you're
Piss?
close. Oh, urine. Yeah, okay. I have no money, I need to feed my family. I'm gonna sell urine. Okay, where's the mercury in the urine coming from? Oh, you know what else was real prevalent? You know what else was?
Plates.
How about STDs? Oh, and how do we treat things like syphilis with mercury back in the day? So everybody's passing around bugs. Everybody's sharing their STDs. Back in the day, it was a lot harder to prevent them than it is now. Today, it is pretty easy to prevent them if you know how to do it. But then, we share all the bugs. We share all the bugs. We don't have any good ways of not sharing bugs. So we share bugs like syphilis. And that made people kooky too, right? But other certain types of STDs and other diseases too, not just STDs, but they were treated with mercury. So then your body processes the mercury. If mercury was like one component of the drugs, right? And then your body processes the mercury and then you expel it in your urine as mercury nitrate. And the milliners go, I need that. Thank you very much. Here's some money. Thanks for your pee. If you've ever heard the term piss poor. Yes. Like that's a piss poor explanation. Piss poor comes from literally being so poor you sold your piss. Yes.
How much per gallon is there?
Do what?
Is it like exact measurement?
No, I don't think they exactly measured it. No, they whatever. Yeah, literally. And then the whole.
You consider doing business?
Yeah, I mean you could. Back in the day before we had like people will criticize today's pharmaceuticals, and we did it earlier. There's a list of 1 million side effects from taking this drug. It's still worlds better than where we were. Yeah. We talked about once like oldest items in this house, like it's definitely that chant over there. But one of my oldest items in this room is this little bottle, which I will not pass around because it is from about 1880. So it's very old. The label is replaced. I found a replaced label and affixed it myself because you can't find them with the labels anymore. It's very rare. But it has a pontial on the bottom, which is how you know if a bottle is really old. This is where it was attached to the rod when it was put in the kiln and they popped it off. You see this little mark on the bottom of a bottle. It's called a pontial. And it's this lovely blue color. This is Godfrey's cordial. This was opium given to babies.
Oh.
Literally, my baby's crying and I can't make him stop. Have some opium. Because, oh yeah, some of them stop crying forever. Literally. So, yeah, it worked real well. It would stop your baby from crying, all right, because they'd be knocked off. Yeah. Yeah.
Maybe
You know,
give it some
maybe.
food.
You know,
Give your baby some food, some attention.
there was a British lady. There was a British lady who was a baby farmer.
Oh,
I think I talked about her, right?
Yeah.
Yes. So yeah. Oh, you poor pregnant unmarried woman. If you just pay me a fee, I will farm your baby out to a family somewhere and no one needs to know of your terrible condition. You horrible human being. We should all look down on you, right?
Mm-hmm.
So you're poor, you're unmarried, you're a woman, you're pregnant, you go to the baby farmer because you don't have any other options. And the baby farmer says, here, pay me some money and I'll take care of this baby for you. And there was one in particular, Amelia Dyer. She took care of them by one after another. Yep. Sequentially poisoned and overdosed many an infant on that exact drug. That one. Godfrey's cordial. No, I hope not. I don't know that bottle, she was English. I don't know if that bottle is from Europe. I don't know where it came from. But yeah, probably did come overseas at some point, but I don't know. But yeah, that's a great example of, yep. Now you can do all sorts of things to make a baby stop crying that doesn't involve giving them opium. But Back in the day, we just gave them opium. All right, now, the junior's homework assignment, and this one's interesting, so I'm gonna share it with you because it's just an additional blurb of information. So the junior's homework assignment, the research they're doing isn't dimethylmercury. They, in particular, are going to research Kevlar. Who produced Kevlar, what it's used for. The person who produced Kevlar is this lady right here, Stephanie Kwolek. And if you want to research something really interesting, the discovery of Kevlar and how it's been used is pretty fascinating. So what is Kevlar used for? You know?
Hockey net guards.
Hockey net guards. Okay, that's a good one. What else is it used for?
Fire hoses and bulletproof vests.
Fire hoses and bulletproof vests. These are all good examples. Yes. Some parachutes. Well, what were you gonna say that too? Yeah. So,
Bulletproof vest.
yeah, that's what he said. The one. Yeah, bulletproof vest. So yeah. So basically, she didn't set out to create exactly what she created. She was trying to create a polymer, like you did in lab today, that had certain characteristics. And the one she created seemed to be like, it was not exactly what she was aiming for, but when she got it, she was like, okay, there's real serious potential for this to be used. And she would send it to their lab for testing, and the numbers came back like the data came back in such a way that she was like, that can't be right. It can't be that rigid and flexible, that strong and flexible at the same time. Like it can't be all these things, because Kevlar feels like fabric. I've seen dog toys made of Kevlar for dogs that are like serious chewers. Yeah, mine will. My little dog is a serious chewer and destroys all of the chew toys for big dogs. Like, oh, get this one for your Rottweiler. He won't destroy it. 10 minutes. Ozzy's got it in 50 pieces. Yeah, he's a monster. So this is Stephanie Kwolek, and she has a really interesting story, and Kevlar is really interesting. So this is just kind of how we're going to wrap up this bit today.
What I love about my work is that I have the opportunity to be creative every day. I love the excitement. There's something about me, it's an inherent part of me, that wants the excitement of invention and creativity. My schooling was somewhat different from what it is today, because we had 2 classes in one room. This was in a public school. Frequently, you'd finish your work and you would hear where someone was having trouble in the next class. You would put up your hand and you would give the answer, especially in math. And this went over like a lead balloon, let me tell you.
She's Hermione Granger.
What you really did was you learned 2 grades at one time. I loved learning and loved learning new things. I found it very exciting. So this probably made me what I am today and what I was for many years. When I entered the workforce in 1946, not many women were being hired, but the few that were, they were hired because there were so few men available. They were at war or just coming back from war. So women were being made offers, but that didn't mean, that the problem was completely solved, because women had a very difficult time after they got jobs, and many women did not stay very long. But I was stubborn, and I decided that I was gonna stick it out and see what happened, and things improved eventually. But I didn't stay just because I was trying to, I stayed because the work was what I wanted to do. It was 1965, and I was assigned to look for this super strong, super stiff, but lightweight fiber. In the course of that work, I made a discovery. The results came back. It was very strong and very stiff. Unlike anything we had made before, I hesitated about telling anyone because it was unusual and I didn't want to be foolish. And so I sent it down a few more times, and it always came back more or less the same numbers. And so I then told my supervisor, and we in turn told the laboratory director, and everybody became very excited. So that was the beginning of Kevlar. I was elated to have made this discovery because most people work a lifetime and they never do anything like this, something that saves human lives. I think the role of science is to improve human life in general and improve the world as well. When I reflect back upon my career, I am inspired by the fact that I was able to do something that was of benefit to mankind.
So Stephanie Kwolek lived to be 90 years old.
She sounded like she was on her dying breath.
She was excited about her story. So she lived to be 90 years old. She died in 2014. So she is contemporary to all of you. All of you have lived the same time as Stephanie Kwolek. Anybody want to guess what company she worked for? I don't think she said in that video. Think of some big chemical. What are the big chemical companies? It's one of the big ones. I can guarantee you've heard of it. Do you think of one? Clorox. Okay, it makes a chemical. I'm talking like the big, like 3M would be an example of a big chemical company. Not 3M. Johnson & Johnson's a good guess. Those are pharmaceutical. ExxonMobil, that's a good guess. All right, so she worked for DuPont.
Oh.
You know DuPont?
No.
Yeah, they make paint, they make everything, right?
Jeff Gordon.
Jeff Gordon, yes, his car was a DuPont car.
Rainbow.
The DuPont family originally, and now it's like a huge conglomerate. DuPont is a massive company. She worked for DuPont, and it is really only because the men were not available because they were all at war and coming back from war that she was even afforded the position in the first place. The DuPont family, by the way, is very philanthropic. Interestingly, the chapel on the Hollins campus is the Jessie Ball DuPont Chapel because she married into the DuPont family and she was an alum. So the chapel we have the DuPont Chapel. But you'll find DuPont on a lot of college campuses, a lot of places you'll see the DuPont name. So she worked for DuPont. But yeah, she's a cool one. She's a really cool one. A contemporary scientist who did something that is really seriously like impacted all of our lives. We've all probably had Kevlar at some point. It's something. Hello, Stephanie. There you go.